Quantum computers represent a distinct class of scientific instrument, operating under physical laws that separate them from standard laptops or supercomputers. Popular media often describes these machines as calculating every possible answer at once. This is a mathematical misconception. Qubits exist in a state of superposition, holding probability amplitudes for every potential outcome. These amplitudes determine the likelihood of a result, but they are only readable as a single bit once measured. When networked, qubits scale the mathematical state space exponentially. An n-qubit system holds 2 to the power of n amplitudes. Extracting this entire space as classical data is impossible. Measurement forces the space to collapse into a single string of zeros and ones. The central engineering challenge is the manipulation of these hidden probability amplitudes before that measurement collapse occurs. To control those amplitudes, we rely on entanglement. This property creates correlations between widely separated qubits that ordinary classical probability cannot reproduce. Interference provides the second critical mechanic. Because quantum amplitudes have phases, different computational paths interact with one another throughout the calculation. Successful quantum algorithms use destructive interference to force the paths leading toward incorrect answers to cancel each other out. Simultaneously, constructive interference aligns the phases of paths leading to the correct answer. This creates a massive spike in probability for the desired result. The machine mechanically sculpts a probability distribution so that the useful answer becomes the most likely outcome upon measurement. Because this process relies on precise phase manipulation, quantum speedup is a highly specific mathematical advantage rather than a blanket enhancement for all software. This chart compares scaling trajectories for integer factorization. For classical computers, required steps grow exponentially with input size. Shor's algorithm allows polynomial growth. This mathematical gap allows a sufficiently capable quantum computer to undermine public key cryptography like RSA. Other advantages are less extreme. Grover's search algorithm provides a modest quadratic speedup, requiring roughly the square root of n checks to search a database. These speedups are strictly bound by their algorithmic structure. Ordinary processors remain superior for unstructured, everyday computing tasks like word processing or web browsing. Transitioning from theory to hardware requires extreme physical control. Currently, the industry has no universal standard for building a physical qubit. Superconducting systems perform operations quickly, but they require temperatures just a fraction of a degree above absolute zero. Heat, microscopic fluctuations, or electromagnetic noise cause qubits to interact unintentionally with their environment. This process, B-coherence, destroys the phase relationships required for quantum logic. The no-cloning principle prevents us from using classical error protection, as an unknown quantum state cannot be copied. Quantum error correction solves this by spreading the information of one logical qubit across a large, entangled web of physical qubits. Google Quantum AI recently demonstrated a distant 7 memory operating below the error correction threshold. At this scale, adding more physical qubits actually reduces errors. This massive overhead makes raw physical qubit counts a misleading metric. Computational power depends on the number of reliable, error-corrected logical qubits the hardware sustains. Current hardware belongs to the noisy intermediate-scale quantum, or NISQ era. These devices lack the full error correction needed for deep circuits. Modern quantum workflows use a hybrid model. A classical computer sends parameters to the quantum processor and uses measurements to update the cycle. Future machines will depend on classical infrastructure to schedule operations and decode errors, functioning as specialized accelerators under a master system. Chemistry and materials science are the most immediate applications for these hybrid loops. Classical methods use approximations that fail when simulating strongly correlated molecular systems in catalysts or batteries. In drug discovery, the quantum processor handles a specific simulation step within a much larger pipeline of AI modeling and laboratory experiments. Success is measured by whether a complete hybrid workflow performs a useful calculation more accurately or economically than the best available classical alternative.